Conditional probability, when one event has already occurred and a second event is being analyzed. I like to call these the given problems. So we write it as probability of A. This means given, so draw you an arrow right there. Probability of A given B, and we'll say it as probability of A given B like that. So we're gonna kind of narrow some stuff down with this, and I'll show you some examples. So we got this chart here, car ownership by grade. We got some juniors and seniors that own cars. We got people that own a car, people that don't own a car. What is the probability that a randomly selected student will be a junior, given that the student owns a car? When you see that word given, I want you to underline that phrase after that. Given that the student owns a car, I want you to come up here to your chart and I want you to circle all the people that own a car. Okay? So we have this chart with all these people that own a car, don't own a car, juniors, seniors, but we're only going to look at the students that own a car. So my denominator is going to be 18. That's the total number of people, given the number of students that own a car. What's the probability that a randomly selected student will be a junior, given that the student owns a car? So we're only looking at these. That would be 1/3. You could write that as 0.33333333. This is what I prefer right there. Okay. You could leave it as 6/18, though 1/3 looks a little bit prettier. Let's slide it over. What is the probability that a randomly selected student will be a senior, given that the student does not own a car? I am only going to look at the people that do not own a car. Okay, so what's the probability that a randomly selected student will be a senior? There's 8 seniors out of 18. That is, what, 4 out of 9? Which would be 0.44444. What is the probability that a randomly selected student will own a car, given that the student is a senior? So this one's a little bit different. We're only going to look at the seniors. So I'm going to look at all of these people right here. My denominator this time will be 20, only looking at the students that are seniors. There's a total of 20 seniors. And the student will own a car, 12 out of 20. And that reduces to 3/5, or 0.6. All right, next one. What is the probability that a randomly selected student will not own a car? This one doesn't say given. Dadgummit. So I guess we're going to look at our total here. What's probably the randomly selected student will not own a car? There's 36 total people there. Well, how many people don't own a car? 18. 18 people don't own a car. 36 total, that's 1/2, or 0.5. What is the probability that a randomly selected student will own a car, given that the student is a junior? We're going to look at only juniors up here. Okay, so my total is going to be 16. What's probably that a randomly selected student will own a car? How many of those own a car? 6 of those 16 own a car. That would be 3 out of 8. Okay. All right, next set. Let's find this sheet that has the spinners on it. All right, we've got Bill spinning 2 spinners that have 5 equal sections numbered 1 to 5. If he spins a 4 on at least one spin, what is the probability that the sum of his 2 spins is an even number? Well, there's a phrase that we just talked about a little bit ago, and it was given. And when we saw given, we underlined that. And that's the only one we looked at. We circled the ones that we were looking for and went from there. So if he spins a 4 on at least one spin, that's like saying given. Given that he spun a 4 on at least one of those spins, I'm only going to look at the ones where they got a 4 in it. So let's look at a picture. I drew it pretty Bad picture right here. But given that one of them is a 4, so let's say that this one's a 4 right here. Given that that's a 4, what are all my other options for this one? Well, I could spin a 4 and then a 1, a 4 and a 2, a 4 and a 3, a 4 and a 4, a 4 and a 5. So let's write those down. And reason I stopped at 5? Stopped at 5 because there's only 5 sections on my spinner. Later on, we're going to have different, 4 sections or 6 sections, or we're going to be rolling number cubes or dice. And, there's going to be different possibilities like that. Right now, we're stopping at 5 because there are 5 sections. So let's go back to this. We wrote down 4, 1, 4, 2, 4, 3, 4, 4, and 4, 5. Looking at my picture, these aren't all of my options because I put my finger right here on 4 and then said, okay, we could do a 4, 1, 4, 2, 4, 3, 4, 4, 4, 5. I've got 2 spinners though. I could start with this one being a 4, since this is a different spinner, spinner number 2. I can say 4, 1 over here, 4 over here, 2 over here, 4 over here, 3 over here. When I get to 4, 4, I've already done that one. But I could say 4, 5, and those would be 2 different results from my spinners. So let's write those down. I could also have 1, 4, 2, 4, 3, 4, and 4, 4 is the same, and 5, 4. So those are all of my options. Given that at least one of those spins is a 4, okay? So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 total options. And we want to know how many of those would have a sum that is an even number. Sum means to add. So 4 plus 1, this row would equal 5. 4 plus 2, this row would equal 6. This row would equal 7. This row would equal 8. This row would equal 9. And I need the sum to be an even number. Well, 4 plus 2, that's 6. 2 plus 4, that's 6. 4 plus 4, that's 8. Those are even numbers. 3 total, that's 1/3. Next, I've got Bob spinning 2 spinners that have 4 equal sections this time. Numbered 1 to 4. If he spins a 3 on at least one spin, that's like saying given that he spun a 3 on at least one of those. So that would mean 3, 1, 3, 2, 3, 3, and 3, 4. That would also mean 1, 3, 2, 3. Can't do 3, 3 again, it would be the same. And 4, 3. So total, I would have 7. So if he spins a 3 on at least one spin, what is the probability that the sum of his 2 spins is a number greater than 5? Well, the sum of 3 and 1 is 4. This would be 5, 6, and 7. Greater than 5. Is 4 greater than 5? No. Is 5 greater than 5? No, it's equal to 5. Is 6 greater than 5? Yes. Is 7 greater than 5? Yes. 3 out of 7. All right. Tom spins 2 spinners that have 6 equal sections numbered 1 to 6. If he spins a 2 on at least one of the spins, what's the probability that the sum of his 2 spins is a prime number? Well, we have 6 equal sections. If he spins a 2 on at least one spin, given that one of them is a 2, will be 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. It would also be 1, 2. Won't do 2, 2 again. Okay, so that would be a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ways that I could roll or spin one of those with a 2. What's the probability that it is a prime number, that the sum will be a prime number? Well, since it's sum, let's add them up. That would be 3. 2 plus 2 is 4. This is 5, 6, 2 plus 5 is 7. That's 8. So the sum of his two spins is a prime number. Prime numbers are numbers that their only factors are 1 and itself. So in this case, 3 is a prime number. 5 is a prime number. And 7 is a prime number. I think that's it. So we got 6 out of 11. All right, let's look at this sheet. It's got independent events up here. And there's a lot of stuff that I don't like about this slide. First of all, I want you to just go ahead and mark out all this stuff right here. We'll talk more about that later. But that is like mathematically incorrect, so we don't really want to look at that. The other thing that I want you to change is this up here. This should say probability of A and B. Okay, so it should be the upside down U. So probability of A intersect B is equal to probability of A times probability of B. All right, once you got those down, we're in good shape. So we're going to look at independent events and we're going to say, are these things independent or not? Okay, we're not going to decide if they're dependent, that kind of stuff. It doesn't really make sense today. We're going to look at very specific examples, just a couple of them. So the probability of event A happening is 0.45. The probability of event B happening is 0.2. The probability of both A and B happening is 0.09. Are the events independent? Okay, we're not going to talk about dependent. Are they independent? Well, up there we said if you multiply them and they give you the same thing of both of them happening, then they are independent. So let's multiply these things. Event A is 0.45 times 0.2. And we want to know, does that equal 0.09? So when you punch that into your calculator, you'll see that that is 0.09. And yes, that does equal 0.09. So let's write yes, independent. Okay. Next one. The probability of event A is 0.3. Event B happening is 0.9. Both A and B happening is 0.25. Are the events independent? Well, let's take 0.3 times 0.9, and we want to know, does that equal 0.25? Punch that in your calculator, you would get 0.27 equals 0.25. Does 0.27 equal 0.25? No, 0.27 does not equal 0.25. Therefore, we're going to say, no, these are not independent. Okay, let's look at next example down here. In a certain town, the probability that a person plays a sport is 65%. Okay, let's go ahead and do this. Let's write 65% as a decimal. It'd be 0.65. The probability that a person is between the ages of 12 and 18 is 40%. The probability that a person plays a sport and is between the ages of 12 and 18 is 26%. Are the events independent? Well, I need to multiply the two regular ones. So we got what? Probability of A times probability of B equals probability of A and B. So the probability of one of these things is 0.65 times probability of the other one, 0.40. Does that equal 0.26? When you punch that in your calculator, you do get 0.26 equals 0.26. Yes, independent. Last one, in a certain town, the probability that the person smokes is 3%. That would be 0.03. The probability that a person is over the age of 60 is 25%, 0.25. The probability that a person smokes and is over the age of 60 is 0.05%. All right, remember, we moved the decimal place twice on this one, twice right here. We got to move it twice right here. So there's going to be another 0 right there. So this would be 0.0005. And are they independent? So we're going to say 0.03 times 0.25. Does that equal 0.0005? When you punch that into your calculator, you get 0.0075. No, those are not equal. No, not independent.